This is the second part of the NPLM in the word embedding series. This video was produced in Korean and then translated into English. The audio was generated by AI text-to-speech. In this video, we will implement a simple NPLM using Keras. First, let's implement the original model presented in the paper discussed in the previous video using Keras. Next, let's implement the NPLM using Keras Embedding layer. Finally, let's implement this model using LSTM and CNN. Since word sequence data is also a type of sequential data, both LSTM and CNN can be used on word sequence data. In addition to these, sequence-to-sequence, attention, and transformer models, which will be covered later, can also be used on word sequence data. Now, let's implement a simple NPLM from scratch using Keras. We will use this very tiny dataset to train an NPLM. This corpus consists of only 5 sentences. First, we build a vocabulary using these sentences. To do this, we used Keras' tokenizer class to tokenize a list of texts or sentences. The method fitOnText updates the internal vocabulary based on a list of texts. This method creates the vocabulary index based on word frequency. The word index attribute of the tokenizer object is a Python dictionary that maps words to their corresponding integer indices. This dictionary is as follows. It has words, strings as keys, and their assigned integer indices as values. The index starts from 1. Index 0 is reserved for pad. If we switch the keys and values in this dictionary, it would be as follows. This dictionary allows you to look up words using integer indices as keys. And the texts-to-sequences method converts the texts into sequences of integers in this dictionary. The sequences converted to integers are as follows. Next, we create n-gram sequences, overlapping contiguous sequences of n tokens. We used 4-gram sequences. NLTK's n-grams class makes this easy. It extracts 4 consecutive tokens using a fixed sliding window. The results are as follows. We use this to generate training data as follows. Xtrain is a matrix consisting of the left 3 columns of this matrix, and Ytrain is the last column vector of this matrix. Xtrain is the input data of NPLM, and Ytrain is the desired output. We will train NPLM to output the word 5 following the word sequence 1, 8, 4. The first row of Xtrain is the cat is, and the first element of Ytrain is walking. Next, we build the model presented in the paper. The word embedding size of the matrix C is set to 8. The vocabulary size is as follows. In our case, the vocabulary size is 12, including index 0. The number of neurons in the hidden layer is set to 64. Create an input layer that receives sequences of words. Since we use 4 grams, the number of neurons in this layer is 3. Next, we create a word embedding layer. The word embedding layer can be implemented using a custom layer in Keras as follows. The input dimension and embedding size are fed into this layer. The input dimension is the vocabulary size, which in our case is 12. The embedding size is the size of a word vector, which in our case is 8. Create a matrix C of size 12 by 8 using TensorFlow's variable. During backpropagation, each element of this matrix will be updated. This model can then generate the appropriate embedding vectors for each word. The call method receives the indices of the words entered in the input layer. Select the row vectors corresponding to the input indices X in matrix C. This is the table lookup in C process, and then return the selected row vectors. This is the tensor X embed of size 3 by 8. None is the batch size. Next, we flatten this tensor into a one-dimensional tensor of size 24. This is the process of concatenating the selected word vectors. Next, we create a hidden layer with 64 neurons. This layer takes as input the tensor X concat. The activation function is the hyperbolic tangent. Next, we create the residual layer and the output layer. The number of neurons in this layer is V, i.e. the vocabulary size. The tensor X concat is input to the residual layer, and the output of the hidden layer is input to the output layer. Add the output of the residual layer and the output of the output layer. This is the final output layer. Apply the softmax activation function to this output. This then outputs the conditional probability given the input sequence for all words in the vocabulary. Now we create and compile the model. And we fit the data to this model. Plot the loss history to see how the model learns and how the loss decreases during training. You can see that the loss decreases like this during training. Next, let's look at the matrix C in the embedding layer of the trained NPLM. Display the embedding vectors for each word in the vocabulary. The results are as follows. Each word is represented as a vector of size 8. These vectors contain syntactic and semantic information for each word. Next, let's see what output we get when we input the sequence "the cat is" into this model. The results are as follows. The sequence "the cat is" most likely followed by the words walking or running. Finally, let's represent the first sentence using the embedding vectors. The results are as follows. This matrix is a representation of this sentence. Let's run this code. We got similar results as in the previous slide. Next, let's implement the NPLM using Keras Embedding class. This makes it easy to create the word embedding layer. We'll use the same data as in the previous code. This time, we will use the embedding layer provided by Keras. The input dimension is the vocabulary size, which in our case is 12. The output dimension is the embedding size, which in our case is 8. Using this layer, we can get the word vectors in the same way as we did previously. The rest is the same as the previous code. The results are as follows. This will give you similar results to the previous code. Next, let's implement the NPLM using a recurrent neural network. In the previous example, the outputs of the embedding layer are as follows. In the feed-forward network in the previous example, we concatenated these outputs of size 3 by 8 to create a one-dimensional tensor. However, when using recurrent neural networks or convolutional neural networks, this output is used as is. Each word vector is input into each time step of the recurrent neural network. Since a word sequence is a kind of time series, it is very reasonable to use recurrent neural networks to learn long-term or short-term dependencies. This figure shows a recurrent neural network with a many-to-one structure. The many-to-one configuration takes a sequence of inputs and produces a single output. This output is fed into the output layer, and the subsequent process is the same as the previous code. This example shows that the word running is activated when the word sequence the cat is entered. Now let's implement the NPLM using Keras LSTM layer. We'll use the same data as in the previous code. The number of recurrent units is set to 64. Create an input layer and an embedding layer. Create an LSTM layer with 64 units and feed the output of the embedding layer into the LSTM. Create a softmax output layer and feed the output of the LSTM into the output layer. The rest is the same as the previous code. The results are as follows. This will give you similar results to the previous code. Next, let's implement the NPLM using a convolutional neural network. Convolutional neural networks can also be used on word sequence data. By applying 1D convolutional filters that slide across the input to detect local patterns and features. While LSTMs are designed to handle long-term dependencies through their recurrent nature, CNNs are often more effective at identifying local features or patterns within the sequence. The output of the convolution layer passes through a pooling layer and is then fed into the softmax output layer. The output layer outputs the conditional probability of each word, just like the previous code. Finally, let's implement NPLM using Keras 1D convolutional layer. We'll use the same data as in the previous code. The number of filters in a 1D convolutional neural network is set to 10. And the size of the filter or kernel is set to 2. Since we use a 4-gram sequence, we set the kernel size to a smaller value of 2. Create an input layer and an embedding layer. Create a 1D convolutional layer with the number of filters and the filter size defined above. And feed the output of the embedding layer into the convolutional layer. Create a global max pooling 1D layer. and feed the output of the convolution layer into it. Create a softmax output layer and feed the output of the pooling layer into the output layer. The rest is the same as the previous code. The results are as follows. This will give you similar results to the previous code. In this video, we implemented NPLM. In the next video, we'll look at Word2Vec,